Our second example has a car traveling at 7 meters per second, accelerates uniformly at 2.5 meters per second squared to reach a speed of 12 meters per second. And this is probably a velocity. It doesn't give a direction, so I'm going to choose the positive direction. So it's speeding up. But actually it didn't start at rest, so time 0 would be maybe here where it already has a velocity, so 7 meters per second. And then some later time, which we don't know what time that is, it had a velocity of 12 meters per second. So we're going to sketch the graphs. And this one I think I'm going to want a little more space in the top half. Okay, so what could I label on my graph? It starts with a velocity here that's positive at the beginning, and then at some later time it has a velocity of 12. So up here. And the slope is the acceleration, which would be 2.5 meters per second squared. And that's a positive acceleration, so this would also be 2.5 meters per second squared. Now, in the velocity time graph, we know that the area would be the displacement, and from here to here, this height would be the change in velocity. So from the initial velocity to the final velocity, that change in velocity went from 7 to 12. So that change in velocity is positive 5 meters per second. I think that's all I can label on that graph. And then the shape of this graph, I can start it at the origin if I want to, but it doesn't have a zero velocity, so the slope can't be flat. It has to start out with some kind of a slope because it already has a velocity of 7 meters per second, and then the slope's going to get steeper. So a curve, but just not starting out flat. Okay, part B, how long does it take for this acceleration to occur? So I have possibilities of using the area here, except I don't know the displacement, so that would give me two unknowns. That's probably not going to work. Or I could try using the fact that I know the slope. I know a couple parts to the slope thing here, so let's try that. Slope equals the acceleration, which is the rise over the run, so it's the change in velocity over the time interval. And I know that the acceleration is 2.5 meters per second squared, and the change in velocity is plus 5, and I don't know the time. Solving for the time, we get 5 meters per second divided by 2.5 meters per second squared, which is 2 seconds. Okay, so now we know that the time here was 2 seconds. And for part C, what is the displacement during this time? I'm going to use the area to find that. So the displacement is the area, and the area here actually looks like a rectangle plus a triangle. So I need the area of a rectangle plus a triangle. And for the rectangle, the base of the rectangle would be the delta t of 2 seconds. And the height of that rectangle is the initial velocity of 7. And then the area of a triangle is 1/2 base times height. So for now I'm just going to write that. I'll do it on the next line. So this comes out to 14 meters plus 1/2 base times height. The base is the 2 seconds, and the height of the triangle is just the change in velocity, which is 5 meters per second. So that gives me 14 meters plus, okay, let's see here. The 2's are going to cancel and the seconds are going to cancel, which gives me plus 5 meters. So the result is 19 meters. Okay, always go back and read the question once you get your answer to make sure that you found what was asked for. What is the displacement during this time? So this would be it, 19 meters during that 2 seconds. So if you looked at this graph, if this is 2 seconds and it started here, then by this time it would be at 19 meters.